Okay, so now let's try designing a lead controller, phase lead controller, for the same plant. So we've got GP here is 1 over S times S plus 2. And our controller now is going to be equal to K times S over Z plus 1 times S over P plus 1, like this, okay? And first, remember I said that I want the pole in the lead compensator to be at a higher frequency, so a bigger number than the 0. And before we had put that 0 at about 8.2. So I'm going to just start by picking P is equal to 20. Okay, so it's further into the left half plane than the 0. And now we go back to that same technique that we're going to place the 0 of the lead compensator to put the closed loop poles at the desired location. So here's the 2 poles from the plant at -2 and 0. And here's my new pole from the phase lead controller at -20. And I have this 0 here that's at a location that I'm going to determine. Okay, it's not going to be at the same place as it was for the derivative controller. And here is the desired location, SD. So the desired location for the closed loop pole is at -1.8 plus pi times j. And so I'm going to draw the vectors like I did before. So I have a vector here, and a vector here, and a vector here, and a vector here. Okay. Now, all 3 of these guys are actually fixed. So I'm going to call this one theta 1, theta 2, and this one is theta 3 here. These are these angles here. Okay, and I already calculated from the previous example that theta 1 is 119.8 degrees, and theta 2 is equal to 86.4 degrees. And now I have this additional phase angle, theta 3, which is going to be equal to arctangent of pi over 20 minus 1.8. And so I get 9.8 degrees. So I get an additional 9.8 degrees from the pole. So I'm going to have a little bit more phase angle from the 0, meaning that the 0 is going to have to be a little bit closer to the origin in order to give me a little bit more phase lead here. So here's the theta from the 0. Okay. So theta from the 0 is equal to 180 degrees minus 180 degrees plus 119.8 plus 86.4 plus 9.8 degrees. And so I get 35.8 degrees. Okay? And if you compare to the PD controller when we were back here, let's see, a little bit further back. Okay, so we didn't have that pole, and so we only needed 26.2 degrees from this 0. So the 0 could be a little bit further into the left half plane. I need a little bit more. I need about 8 degrees additional phase lead to compensate from the extra phase that's contributed from that 0. Okay. And so when I calculate the new location from the 0 using the same technique as I used in the previous example, I solved and we found that Z has to be at 6.16. Okay, so it's closer to the origin. And now I can find the gain. Okay, so we'll find the gain K. And to do that, I'm going to use the equation, right? 1 over K is equal to f of S evaluated at S equals the desired pole location. And so that's equal to L over M1 times M2 times M3. And those lengths are these guys, right? So I have M1, M2, M3, and this one is L, right? So it's the lengths of all these vectors that I'm calculating. And so if I plug in numbers, I have L is equal to square root of pi squared times 6.16 minus 1.8 squared. That's equal to 6.21. And M1 is, I already calculated in the previous example, M2, 3.62. So both of these are from previous PD design. And M3 is the length of the vector to the new pole. So it's pi squared, sorry, it's pi squared plus 20 minus 1.8 squared. So that's 18.5. And so if I solve this now, I get K is equal to M1 times M2 times M3 over L, and I get 18.5. Oh, sorry, no, I didn't say no. 18.5 was M3. I get 34. Okay, so now my new compensator, GC of S, is equal to 34 times S over Z plus 1 divided by S over P plus 1. And actually, I should plug in the numbers there, sorry. S over 6.2 plus 1, and S over 20 plus 1. So that's my phase lead compensator. Pretty easy, huh? And I can, now if we draw a root locus for this guy, I'll just do it rather quickly. So we have the, there's the plot, and I'm going to put the 0 and minus 2, and there's a 0 at minus 6.2, and I have a pole at minus 20. Okay, and now I'm going to draw the root locus points in black. So it's on the real axis to the left of one pole and to the left of 3 poles and zeros in here. Okay, and so it turns out that what happens is that this pole is actually going like this, and these two guys come together and they break apart. They break apart like this, and they will eventually follow asymptotes that take them up this way. Okay. So because there's only here we have n equals 3 poles and m equals 1, 0. We have n minus m equals 2 poles go to infinity. Okay, and they do those along asymptotes. The asymptotes, when we have 2 excess poles, the asymptotes are at plus 90 degrees, and either we could write it as minus 90 degrees or plus 270 degrees, however you are happier with that. And the position of those asymptotes, if we calculate their centroid, we calculate by summing all the poles together and summing all the zeros together. So we get minus 20, minus 2, minus 0. Those are all the poles. And I'm going to subtract the 0, which is at minus 6.2. And I divide by n minus m, so 3 minus 1. So when I do this calculation, I have the location of the asymptotes is at 22 minus 6.2 divided by 2, so that's about 16. I'm going to write it as more or less 16 over 2, so it's about at minus 8. I think that's right, isn't it? Minus 22 minus, if this was minus 6, it would be exactly right. Okay, so it's at about minus 8. So if I draw this a little bit more carefully, let's go ahead and draw where those asymptotes are. They're going to be here, right at minus 8 here, to the left of where this 0 is. So I'm going to redraw this stuff. And so what happens is that these guys will sort of come over this away. Should be symmetric. Something like this. And our desired pole location, which is sort of here at minus 1.8 plus j pi, is definitely going to be on the root locus. Okay? So the PD compensator will do like the phase lead compensator, like the PD compensator, will pull the roots to the left. Okay, so we started out like before I had this compensation, they would have gone straight up like this. So now we've bent them more. We've increased their damping. But it doesn't quite look like the root locus looks a little bit different than it did for the PD design. Like the PD design, if I had drawn the whole thing, this would actually be a gigantic circle that comes down and intersects the real axis. Okay. All right, enough for this week. And next time I'll talk about PI compensation and steady state error and phase lead compensator. Okay. Thanks a lot. Bye.